Hello and welcome. In this video, we'll talk about Markov chains, which are a particular type of stochastic process. Okay. So to take a formal definition, a Markov chain is a stochastic process that firstly exhibits the Markov property, which means that the future states can be completely predicted based on the present, and the past does not provide any additional information for the prediction of the future. Okay. That's the first thing. It has to satisfy the Markov property. Second is that it has a discrete state space. And the third thing is that it operates in a discrete time domain. Okay. So any Markov process with discrete state space and a discrete time domain is called as a Markov chain. Okay. Now let's take an example of this. We have already taken an example of this, and let's just continue on that. The most common and the popular example is the no claim discount scheme, or which is called as the NCD model, right? So the NCD model is used in general insurance to incentivize the policy holders not to make a claim. Okay, so you want to charge the policy holders who do not make a claim a lower premium, that is, we offer them a discount. So for example, let's say there is a general insurance company which is issuing a car insurance, okay, and the total amount of premium is rupees 1000. Okay, that's the total amount of premium, and that is the premium every policyholder starts at. But if you do not make a claim, you get a discount. So this can have for example 3 states. You can have 3 states. The same example that we took in the last section relating to stochastic processes. Let's just continue on that example. So you can have 3 states. You can be on 0% discount. That is, you are not getting any discount and you are paying 1000 rupees of premium, right? Then you could have gotten a 25% discount, and the third state was that you could have gotten a 40% discount. Okay, so every policyholder has to start in this 0% discount level. Okay, and then if they do not make a claim, they move to 25%, and then again if they do not make a claim in the subsequent year, they move to 40%. Okay, so how does this work? So if I am in a particular year at the 0% level of discount, I'll move to 25% if I do not make a claim. So no claim means I move to 25%. Then in the subsequent year, if I do not make a claim again, I move to 40% discount, right? And this is the maximum level of discount. So if I do not make a claim at 40% level, I stay at this level, right? Similarly, if I make a claim, I move down one level. So if I'm at 40% discount, I'll move down one level if I make a claim, right? And if I'm at 25% level, I'll move down one level if I make a claim. But 0% is the lowest level. This is the full premium that you'll have to pay. So this will from this you cannot move down, right? So even if you make a claim, you stay at 0% level. Okay, so this is the consideration here. Now say supposedly we know from the past data that the probability of any claim is 0.25. For a particular policyholder, the probability of making a claim is 25%. Thus the probability of no claim would be 75%, right? So I have these probabilities. So the probability of making claim in any year is 25%, and the probability of making no claim would be 75%. Now let's just replace these situations of claims and no claims with their probabilities. So I had a claim here. So this is replaced with the probability of a claim, that is 0.25. And this is replaced with the probability of claim, that is 0.25, and this is replaced with the probability of claim, that is 0.25. Okay, similarly here, let's just replace this with the probability of making a no claim, that is not making a claim, that is 0.75, and this is again 0.75, and this becomes 0.75. Okay, so we have this diagram which shows that what is the probability of transitioning from one state to another in any particular year. So what is the probability of transitioning from 0% to 25%? It is 0.75, right? And that is how it functions. Okay, so this diagram, which shows all the probabilities relating to a Markov chain, that how it can transition from one state to another, is called as a transition graph. Transition graph or a transition diagram. So a transition diagram is a good way of representing a Markov chain. It shows the one-step transition probabilities of a Markov chain. That means what is the probability of going from one state to another in just one step, that is in 1 year. So for example, if you are at 0% discount in a particular year, 0.75 is the probability that you will be at 25% discount level in the next year, and 25% is the probability that you will be at 0% level of discount in the next year. Similarly, if you are at 25% level of discount, 0.75 is the probability that you will be at 40% next year, and 0.25 is the probability that you will be at 0% next year. Okay, so that is how a transition diagram is read. Now another way of representing the transition probabilities of a Markov chain is a transition matrix. So let's look at that. So as the name suggests, the transition matrix is a matrix or an array of the transition probabilities. So it looks somewhat like this. Each row is represented by an I. Okay, each row is represented as an I, and I is basically the initial state or the state in which you want to begin. Okay, so starting state. And each column is represented by J, which is the state you want to get to. So J is your final state, right? So here in this case, what will the transition matrix look like? I can be three things. I can be 0%, 25% or 40%. Let's call these states as 0, 1 and 2. I'm giving these states some names, 0, 1 and 2. So this is state 0, the 25% is 1 and 40% is 2. So you can start at 0%, that is state 0. You can start in 1 or 2. Okay, three possibilities. And the final state can also be 0, 1 or 2. Now a transition matrix will represent the probabilities of going from state I to state J. Okay, so the first row and the first column, that is the first entry, would represent the probability of going from state 0 to state 0 in one step. So getting from 0 to 0 is 0.25 as shown in the transition diagram 2. Okay, it's 0.25. The arrow pointing from 0 to itself is 0.25. The probability of going from state 0 to state 1 is 0.75. Okay, so the arrow shows that you can go from 0 to 1 in 1 year, that is 0.75. And the probability of going from state 0 to 2, now there is no direct arrow from 0% to 40%, right? That is, if a particular policy holder is getting no discount or is at 0% level of discount in this particular year, in the next year he cannot directly get to 40%. He'll first have to go through 25%. So it is impossible to transition from 0% to 40%. There is no direct arrow. So this probability becomes 0. Similarly, if you are at 25% discount, that is I is 1. So if you want to go from 1 to 0, the probability is 0.25 as shown here. Okay, so this probability becomes 0.25. Then if you want to get from 1 to 2, so there is an arrow from 1 to 2, that is 0.75. So the probability of going from 1 to 2 is 0.75. So if you are in 1, if you make a claim, you get to 0, the probability is 0.25. And if you do not make a claim, you get to state 2, the probability is 0.75. And staying from 1 to 1, if you want to go from 1 to 1, the probability is 0. And the reason is it is impossible to stay in 1, right? So there is no arrow from 1 back to 1, right? Similarly for 2, if you are in 2, the probability that you stay in 2 is 0.75, right? If you make a claim, you will get to 1, the probability is 0.25. So there is an arrow from 2 to 1, 0.25. And it is impossible to get from 2 to 0 in one step. So this one is 0. Okay. So that is your transition matrix. Okay. This is what a transition matrix looks like. And this is how we will be dealing with the mathematics of Markov chains. So let's get into that in the next section. But before that, I would like to point out a few properties of this transition matrix. So each element of a transition matrix is a probability of transition from state I to state j. That is from the state represented by the row to the state represented by the column. So each element can be written as Pij. Okay, it can be written as Pij. Okay, and since it is in one step, we can also write it as Pij1, which is also written as Pij, just Pij, right? So each element is that. Okay, now if you see the rows, okay, the sum of each row of this transition matrix is adding up to 1. See, 0.25 plus 0.75 is 1 in the first case. In the second case as well, 0.25 and 0.75 is 1. And even in the third case, 0.25 plus 0.75 is 1. Now, why is that? See, these events, they are mutually exclusive and exhaustive events. That means that if you are in state 0 in the first year, you'll either be in 0, 1 or 2. Okay, you'll have to be in any of these states in the next year. Okay, so these are all the possible outcomes and they cannot happen together. Okay, so their probabilities will add up to 1. So I can write that probability Ij for all possible values of j, that is 0, 1 and 2, or possible values of j, if I add it over all the possible values of j which belong to S, because these are all the possible values of j that belong to my state space. If I add them up, it will always come out to be 1. So the sum of each row of a transition matrix is always 1. That is something you'll have to remember. Okay. Now let's move on to how the mathematics of the Markov chain works. Okay. Now let's just look at an example in order to understand that how do we calculate the probabilities of transition in a Markov chain. Okay. So the example I'm taking here is of a HSCD model. That is a healthy, sick, critically ill and dead model. Okay. This is an extension of the healthy, sick, dead model that you have seen in subject CT5. I have just introduced another state that is called as critically ill. And this is a HSCD model that is operating in discrete time. So usually you'll expect your healthy, sick, dead model to operate in continuous time. That is, a healthy person can get sick at any point of time. A sick person can fall critically ill at any point of time. Okay. So it can happen at any point of time and not discrete time points. But then here I'm assuming that it happens only at discrete point of time. That is, I'm recording the transitions at the end of every year. So I have a population and I'm checking it only at the end of each year. So I would know about the transitions only at the end of each year. Okay. So this is a discrete time HSCD model. Okay. I'm assuming that. Now let's try to see how it will work. Let's assume that a person can get from healthy to sick, okay, and then they can get from sick, recover from sick to healthy, okay. Now a sick person can die directly, a healthy person can also die directly from either of these states, okay. The next thing is that a healthy person can fall critically ill directly and a sick person can also fall critically ill. But if you are critically ill, you cannot come back from this state because I'm assuming the critical illness is chronic and there is no recovery out of it. Okay. And from the critically ill state, you can only die. Okay. And from the dead state, no one can come back because dead people do not come back to life. Okay. So this is my entire model, HSCD. Okay. Now, for example, let's say I am at time 0, I am in the healthy state. Okay. That is, I'm beginning, my policy holder is beginning in the healthy state at time 0. And at time 2, I want him to get to the dead state, right? I want to calculate this probability of getting from healthy state to the dead state from time 0 to time 2. So this can be written as, this probability is usually written as probability of getting from healthy state to dead state from time 0 to time 2. So 0, 2. That's how you represent it. So let's say I want to calculate this probability. Okay. Now let's look about how I will do it. Okay. So I want the person to be healthy at time 0, and at time 2 I want him to be dead. So how can this transition occur? Okay. There will be intermediate times which are 1. Okay. So I want him to be dead by this time, and there will be transitions in the middle. So let's see how will it occur. So from the healthy state, by the end of the first year, I can get to the sick state, and then this person can die. Okay. So this person can first get from healthy to sick and then die. Okay. Or he can remain from healthy, and then in the next year as well, he remains healthy and then he dies. Okay. Or he can get from healthy to critically ill and then he can die. Right? This is the third possible chance. Okay. So healthy to critically ill and then die. Or in the first year itself, he dies. Okay. So he'll remain dead in the next year as well. Okay. So this is how my model can function. Okay. So if I want the probability of getting from healthy to dead, he can, at the intermediate time, this 1 is the intermediate time. He can either be sick, healthy, critically ill or dead. Okay. And the first and the final outcomes are already given. We want the probability of those. So this probability can be written as, the probability that the person gets from healthy to sick state from time 0 to time 1. I'm talking about the first possible outcome. Okay. I'm talking about the first possible outcome. He gets from healthy to sick from time 0 to time 1. And then gets from sick to dead from time 1 to time 2, right? This is one possible outcome. Okay. Then other possible outcome. So we add. Okay. Because in probabilities, addition means or. Okay. So this happens, or the second thing happens. That is, he gets from healthy to healthy, right? Between 0 and 1. So he does not transition. And then he gets from healthy to dead directly in the second year. So probability healthy to dead from 1 to 2. And then the third possibility is that he gets from healthy to critically ill in 1 year, and then he gets from critically ill to dead from time 1 to 2. Okay. And the next possibility is that he gets from healthy to dead in 1 year, and then he stays dead in the next year. Probability that he stays from dead to dead in the next year, that is from time 1 to time 2. Now this probability of staying dead from time 1 to time 2, this is basically equal to 1, because it is a sure event. A person who is dead at time 1 will remain dead at time 2 as well. So I can write this as 1. Okay. So I need not write it. So this multiplied by 1 is just this thing. Okay. So this is my probability that I wanted. If I want to go from healthy to dead state from time 1 to 2, I can go in all these ways, and all these possible outcomes are added. So this equation that I've written for this probability, this equation is referred to as the Chapman-Kolmogorov equation. So this basically says that if you want to get from any state I to any state j from time m to time n. So here I have represented my time, and here I have represented my Markov chain that is in these states. Okay. Here in the last example, my m was time 0, n was equal to time 1, n was equal to time 2, because I wanted to get from time 0 to time 2, and my state I, the initial state, was healthy, and my final state J was dead. Okay, if I want to go through this transition, so I can take any intermediate time L. In the last example I had taken L as 1. Okay, so I can take any intermediate time L, and if there I am in state K, to get from I to J from time M to N, I'll first have to transition from I to K, from time M to L, and then transition from K to J from time L to N. Okay, and this K, it can be any state which belongs to S. So I can transition for multiple possibilities. So this in the last example, this K could have been the healthy state, it could have been the sick state, it could have been the critically ill state, and it could have been the dead state. Okay, and then I'll have to add all these possibilities. So how do I represent this mathematically? Probability of getting from I to J from time M to N can be written as the probability of getting from I to K from time M to L, okay, and then transitioning from K to J from time L to N, okay, and this is to be added over all the possible values of K. Okay, so basically all the possible values of K that belong to S. Here I had done a similar thing. I had added all the over all the possible values of K. So in the first case I have added when K is equal to the sick state. In the second I have added when K is equal to the healthy state. In the third one, my K that I have taken is the critically ill state, and in the fourth case the K is the dead state, right? So I have to add over all these possible values, and this is the generalization of the Chapman-Kolmogorov equation, right? This is what is the Chapman-Kolmogorov equation, right? Okay, so now in this chapter we'll be discussing two types of Markov chains. The two types are time inhomogeneous Markov chains and time homogeneous Markov chains. Okay, so let's try to understand what these mean. Okay, a time homogeneous Markov chain is any Markov chain in which the transition probabilities only depend on the duration and not on the initial time. Okay, so let's see what do I mean by this. So for a time homogeneous Markov chain, probability of transitioning from any state I to J from time 3 to 5, okay, that is over a span of 2 years, would be same as the probability of transitioning from state I to J over the span of 2 years, let's say from time 10 to 12, and it would be same as the probability of transition from 100 to 102. Okay, so if the duration is equal, if it is just 2 years, it is just the same. This would be same as the probability of transition from time 0 to 2, right? So in all these cases the gap is of 2 years. Okay, so in general I can just write that the probability of transition from I to J over 2 steps, okay, these are all equal to probability of transition from I to J over 2 steps, and they are all equal. So we just care about the duration and we do not care about the time when we start. So it does not depend if you start at time 3, if you start at time 10, time 100 or time 0. Your probabilities of transition from state I to J for 2 steps would all be equal. So generalizing this, if I want to represent it generally, so probability of transition from time I to J from time from state I to J from time let's say the same notation we had taken in the last part, so from time M to N is same as the probability of transition from I to J in the duration N minus M. It would be same, it does not matter when is the time you start. Okay, so I can represent it like this. This is what a time homogeneous Markov chain is. Okay, so I can write generally that a time homogeneous Markov chain is one where transition probabilities depend only on the duration and not the starting time. So I don't care when I start, but if the duration is equal, the probability would be the same. For time inhomogeneous equation, probability that ij from 3 to 5 will not be equal to probability of shifting from I to j from 10 to, this is 10 to 12, okay, from 10 to 12 will not be equal to shifting from I to j from time 100 to 102 will not be equal to transitioning from I to j from time 0 to 2, right? These will not be equal because the transition probability will also depend upon the time when you start, okay? So over time the probabilities change, okay? So I can just write it as where transition probabilities depend on duration as well as starting time. So if you see this carefully, okay, for a time homogeneous process, or a time homogeneous Markov chain, my Chapman-Kolmogorov equation changes. Now it only depends on duration. So Pij over the duration, okay, what would be the duration here? N minus m, okay. So Pij over the duration n minus m is equal to the probability of transitioning from I to k over the duration L minus m, and then transitioning from k to j over the duration n minus L, okay, and this is added over all the possible states k that belong to S. So this is the Chapman-Kolmogorov equation for a time homogeneous Markov chain, okay, where the transition probabilities only depend on the duration and not on the starting time, okay. And in this chapter mostly we'll be talking about time homogeneous Markov chains, okay. So even for the NCD model, we will assume that the probability of making a claim between time 0 and 2 is same as the probability of making a claim between time 2 and 4, okay. So that will be our assumption with this chapter, that the the Markov chains are mostly time homogeneous. We will be dealing with a few time inhomogeneous models, but their mathematics in this chapter is not covered in detail. In detail we'll only cover time homogeneous Markov chains, right? So the transition probabilities will only depend on the duration of transition and not on the initial time when we start. Okay, so now we know that we are dealing with time homogeneous Markov chains, and we know about the theory of the Chapman-Kolmogorov equation. So let's try to apply that in order to find the transition probabilities from one state to another. So how do I do that? For example, I want to go from state I to j, okay, in let's say 2 steps, okay. So for 2 years I want to do this, okay. So how will I go about doing this? I'll add over all the possibilities, I'll add over all the possible values of k that belong to S, that is all my possible states, and I'll go from I to k in one step, and then I'll go from k to j in one step, right? And these one step transition probabilities I already know that they are given in my transition matrix, okay. So if you want to calculate the Z step transition probabilities, You just need to multiply the one step transition probabilities z times. Okay, let's take a question and try to see how do we go about doing it. How do I calculate the z step transition probability if I want to for a given Markov chain? Okay, so let's take an example. For the originally discussed NCD model, calculate the probability of transitioning from state 0 to state 2 from time 0 to 3. Okay, this is what I want to calculate for my original NCD model, that is the probability of a policyholder getting from 0 to 40% discount, state 2 was 40% discount in 3 years from time 0 to 3. Okay, so how will I go about calculating this? Let's just first write the matrix of that model just so that you can recall it. Okay, so I had states 0, that was 0% discount, I had 25% discount, and I had 40% discount, right? And I had 0%, 1 and 25% and 40% discount, right? So this was my model, and the probabilities were that I could go from 0% to 25% with a probability of no claim, that was 0.75, stay here with a probability of 0.25. Then I could get from 1 to 2, okay, so that was the probability was 0.75 for going ahead, and for going back it was 0.25, and you could not stay in state 1. And the probability of staying from state 2 to 2, that is if you do not make a claim, that is 0.75, and coming back to state 1 is 0.25, and you cannot go from 2 to 0, so this probability is 0. Let's also draw the transition diagram. So the transition diagram looks somewhat like this. You were at 0%, you were in state 1, that is 25%, and then at 45%. So getting from 0 to 1 was possible, and it had a probability of 0.5, that is not making a claim. Okay, all the forward arrows are not making a claim, and thus they are 0.75. 1 to 2 was also 0.75, and then you could stay in 2, so that was also 0.75. Now if you are in 0, if you go down, you stay in 0, so that is 0.25. If you are in 1, you go down to 0, that is 0.25, and then if you are in 2, you can go to 1, that is 0.25, right? So this is what your transition diagram looked like. Now let's try to solve this probability, okay, and there are 3 methods to do it. So I'm going to discuss all 3 methods. Now I have method number 1, that is through the Chapman-Kolmogorov equation, just like we did in the last part with the HSCD model. Okay, method 1 is Chapman-Kolmogorov equation. Okay, and this is just your probability common sense, the way I'm going to do it. Okay, so what I want is I want to be in state 2 at time 3, right? Time is 3 and state is 2, and initially I am at time 0, I am in state 0. Okay, so this is what I want, right? So how can this happen? Let's write all the possibilities for this. Okay, looking at the transition diagram, let's try to see all the possibilities. So I can get from state 0 to state 2, okay, between time 0 and 3, right? This is what I already have given. Okay, now what will be the intermediate times? The intermediate time would be 1 and time 2, right? Because the transition is already possible at discrete points of time, that is at the end of each year. So time 1 and time 2. Okay, so this is my time. Now how do I transition? Okay, the first way is that I stay from 0 to 0, and then in the first year I transition from in the second year I transition from 0 to 1, and in the third year I transition from 1 to 2. Okay, so the intermediate state become I stay from 0 to 0, and then I transition to 1, and then I transition to 2. And this is how I can go about it. Okay, this is one way. The second way is that I can go from 0 to 1, okay, and then I can go from 1 to 2, and then I can stay in 2 in the third year. So I'm in 0 at time 0, then I'm in 1, then I can go to 2 and then stay in 2. Okay, Is there any third method? There is no third method. You could have thought of one more, which was this. Okay, you could have thought of one more, which was this. If you are in 0 at time 0 and time 3 you are in 2, you could have gone to 1 and then stayed in 1 and then gone to 2. Okay, so 0 to 0 and then 1 and then you stay in 1 and then go to 2. But this is not possible because you cannot stay in 1. If you are in 1 in any year, you either go to 0 if you make a claim, and if you do not make a claim, you go to state 2. So a transition from 1 to 1 is not possible, and this is indicated since there is no arrow from 1 going back to 1, right? So that is why this transition is not possible. So this transition is not possible. So you just have two possibilities and you just need to multiply the probabilities and add them for these two. Okay. So probability of getting from 0 to 2 between times 0 and 3. This can be written as probability of getting from 0 to 0. Okay. In the first year. So that is 0 to 0. That is 0.75. No, 0.25. Right. 0 to 0 is 0.25. And then you go from 1 to 0 to 1, right? So if you go from 0 to 1, that is 0.75, and then you go from 1 to 2, that is again 0.75. So this is one possibility. This is this one, the first one, and you add the second one, which is going from 0 to 1, that is 0.75, then going from 1 to 2, that is again 0.75 because you're moving ahead, and then staying in 2, if you check that probability, it is 0.75 again, right? So that is also 0.75. So your final answer for this would come out to be 9 by 16 or 0.5625. So this was one method of solving it using the Chapman-Kolmogorov equation. Okay, let's see the second method. Second method is matrix multiplication. So for this you will have to remember how to multiply the matrices. Right? You will have to know how to multiply the matrices. Okay. So let's see how do I do that. Okay. So if I want to get from 0 to 2 from time 0 to 3, okay, if I want to do that, okay, so this is a 3-step transition probability. Okay, so for that what I'll have to do is I'll have to take a cube of the matrix P. I'll have to take a cube of the matrix P, right? So my P here is it is 0.75, 0.25, 0.750, 0.75, 0.250 and 0.75, 0.25 and 0. This is my P. For this I'll have to take the cube of P. Okay, if I want to go from 0 to 2 from time 0 to 3, I'll have to take a cube of P because it's a 3-step transition probability, and then I'll have to take the column corresponding to I is equal to 0 and j is equal to 2, right? So that is column, I'll have to take the value corresponding to I is equal to 0 and j is equal to 2. That is the initial state is 0 and the final state is 2. So I've got 0, 1 and 2 here and 0, 1 and 2 here, right? So which value I'll have to take? So from 1 to 2, so this is the corresponding value that I'll have to take. So I'll have to first cube the matrix, and then I'll have to take element number, first row and third column. So that is 1, 3. So this is one way of calculating it. You just have to multiply the transition probabilities matrix and then you have to take the value 1, 3. Okay, this is one way. So how do I do that? Let's see how do I do that. And this method is very lengthy and complicated. Okay, it takes a while to solve this, but let's also see this method as well. Okay, so I have my initial matrix P and I have to calculate P cube. So for that I'll first calculate p square. Okay, so I have my p here, right? First thing I'll calculate is p square. So p square is basically p into p. I'm forward multiplying p with p. So how do I do that? Let's just see. This is 0.25, 0.75, 0, 0.25, 0, 0.75, 0, 0.25 and 0.75. Okay. So this is another method that I can use, matrix multiplication. Okay. So I'm calculating p square first and then I'll calculate p cube. So just multiplying 0.25, 0.75, 0, 0.25, 0, 0.75 and 0, 0.25, 0.75. Now in case you have forgotten matrix multiplication, I'm going to teach it to you, okay, and then you can practice by yourself. If you do not get it, just try to watch a few YouTube videos on this topic, matrix multiplication. It's very basic, it's usually covered in high school, okay, it's very easy. So how do I go about doing that? So for the first element of this matrix p square, I'll have to multiply the first row of the first matrix with the first column of the first matrix. So I just multiply 0.25 with 0.25, okay, and then add. Okay, now I multiply the second element of this row with the second element of this column. So that is 0.75 into 0.25, okay, and then the third element with the third element. So that is 0 into 0, right? So multiplying the first row with the first column gives me the first element. Similarly, I can calculate the second element of this row multiplying the first row by the second column. So that becomes 0.25, 0.75 plus 0.75 into 0 plus 0 into 0.25, right? So on and so forth. So this is how you'll keep on multiplying. Here you'll multiply the first row in the last column. Then you'll when you get to this level, the element 2, 1, so you'll have to multiply the second row with the first column in order to get this one, and so on and so forth. And you can just multiply and add all of these to get all these elements, and your final matrix p square would come out to be, if you'll solve this, it will come out to be, please solve it by yourself, it will come out to be 1 by 4, 3 by 16 and 9 by 16, and then it will come out to be 1 by 16, 3 by 8 and 9 by 16, okay, and the last one it will come out to be 1 by 16, 3 by 16 and 3 by 4, right? So this will be your p square. The next thing I need to do is calculate p cube, which would be p square times p, okay. So you'll have to multiply p square forward by p, right, or you can multiply p by p square, same thing, okay. So if you multiply this, your value for p cube will come out to be, okay, so this is your state 0, 1 and 2, again this is your state 0, 1 and 2. So if you multiply these two, do it by yourself, multiply p with p square, and these value will come out to be 7 upon 64, this one comes out to be 21 by 64, this one comes out to be 9 by 16, this one here comes out to be 7 upon 64, this comes out to be 3 by 16, then this is 45 by 64, this one is 1 by 16, then you have 15 by 64, and then you have 45 by 64 again, okay. Now which element did I need? I needed the element of going from 0 to 2, right? So 0 and 2, right? This is my initial state I and this is my final state j, okay. So I'll have to take the first row and the third column, so that is 9 by 16. So p P02 in 3 steps, 0 to 3, this one would come out to be 9 by 16, and it's the same probability that we had gotten earlier, right? So it's the same probability that we had. So this is the second method. Now let's try the third method. So before we start with the third method, I want you to understand something. If we want to calculate the n step transition probability from state I to state j, it is just a product of one step transition probabilities n times, right? So I can get the n step transition probabilities by multiplying the one step transition probabilities n times. Okay, so if I want to calculate these transition probabilities and I want to model a time homogeneous Markov chain completely, I would want two things. The two things are the initial distribution. What does this mean? The initial distribution is the state or the states we begin in. Okay, so at time 0, what is the distribution of the Markov chain? Okay, that is something I would like to know. Okay, so what is x0? What is the value of the random variable x0? So where do we begin? In our previous example, all the policyholders began in the 0% discount state. Okay, so everyone was at 0% discount and paying full premium. We knew that because everyone starts with a full premium of 1000. So in our example, our initial distribution can be represented as a vector. Okay, now I am trying to represent everything as a vector in the third method. So my initial distribution, that is x0, it can be represented as a vector, okay, with probabilities 1, 0 and 0. Okay, so this is corresponding to state 0, 1 and 2. So my probability of being in state 0 is 1 because all my policyholders will begin in state 0. That is, in every case my policyholder will begin by paying full premium. Okay, and the probability of beginning in state 1 and state 2 is 0. We could also have situations where we have probabilities of beginning in state 1 and state 2. Okay, so the question could have told you that the probabilities that the people begin at 40% or 25% discount can also be something. For example, if we conducted some initial check about the drivers while issuing them the car insurance policy, and if we check their past data and based on that we are giving them some initial discount. Okay, so they could have told us that 50% drivers begin in the 0% discount state and 25% drivers begin in 25% discount state, that is state 1. Okay, and 25% people begin at 40% discount state. This is one example. So they could have told us something like this. Okay, so this would have been my initial distribution, that is x0, right? So my initial distribution at time 0 becomes x0 and it can be anything. In this case it is 1, 0, 0 because all my policyholders are beginning in the 0th state, that is at 0% level of discount. And the other thing that I need is the one step transition probabilities. That means the transition matrix. So if I have the transition matrix for the Markov chain, I have the one step transition probabilities. So I can calculate the n step transition probabilities by multiplying the one step transition probabilities. So these are the two things that I need, right? And based on this, I'll start with my third method. So my third method is vectors approach, right? Here I'll look at the distribution of the Markov chain at any particular point of time as vectors, just like I did in the last section. So my x0, that is my distribution of the random variable at time 0, is 1, 0, 0. That means all the policyholders are in the 0% discount state and there are no policyholders at 25% or 40% discount level, right? And if I want to calculate the next level probability, that is x1, that can be calculated as I'm in x0 already, and then I'll multiply the transition probability with it, which is contained in the transition matrix. So that becomes x0 into p. So I'll multiply this vector with the matrix p. So how does that function? Let's look at that. So 1 0 0, and I'm multiplying this with p, forward multiplying it with p, right? So p was for state 0 1 and 2, it was 0.25 0.750, and then for the second line it was 0.75 0 0.25, and the third line was 0.75 0.25 and 0, right? So this was my matrix P, right? Now let's multiply these two. So this will give me my x1, that is the distribution of this stochastic process or this Markov chain at time 1, right? So if I multiply this, this becomes multiplying 1. Now how will I multiply this? 1 multiplied by 0.25, then 0 multiplied by 0.25. So I'm multiplying, considering this x0, the vector, as a row and multiplying it against the column. So it becomes 1 into 0.25 plus 0 into 0.25 plus 0 into 0. This would give me my first element, right? And then for the second element of this, okay, I'll multiply 1 by 0.75 and 0 by these two values. So that would just be 0.75. And for the third element, I'll multiply 1 with 0 and then these two other values with zeros and zeros. So this would be 0. So my value for this vector would come out to be, if I check it, it is just the first row of this matrix. It is 0.25, 0.75 and 0, right? So basically what this is saying is that if I was in state 1, in state 0, that is at 0% discount at time 0, right? So my probabilities for time 1 would be, I'll be in the 0th state, that is at 0% level of discount with a probability of 25%, and at the 25% discount with a probability of 75%, right? And this is logical because we know that if I was in the 0% state, I could transition to the 25% level of discount if I do not make a claim, and that probability is 0.75. And if I make a claim, I'll stay in this state, so that is 0.25, right? So that is how I got this. Now next level, at time 2, I'll have x2, which would be same as x1 into p, right? So I'll multiply x1 and then transition it using p. So again this becomes 0.25, 0.75 and 0, and this is multiplied with this matrix that was 0.25, 0.75, 0, 0, 0.25, 0.75, and then 0.75, 0.25 and 0, right? So let's just multiply them again, which would give me my probabilities at time 2. What would be my probability of being in any of these states at time 2? So let's see that. So if I multiply them, 0.25 into 0.25, 0.25 into 0.75 and 0 into 0 I'll add all of them up. So the first element would be 0.25 into 0.25 plus 0.75. Just multiplying this, considering this as a row and multiplying it with the first column would give me the first element. So 0.75 into 0.25 and then plus 0 into 0. So all I'm saying is that if I am in state 0, the probability that I'll stay in state 0 would be equal to this. The probability, if I'm in state 1, the probability that I'll come back to state 0 would be this, right? So I'm just multiplying these two probabilities for getting my probability of being in state 0. And if I'm in state 2, okay, my probability of coming back to state 0 would be this, right? So these two are multiplied as well, right? So that is why I'm doing it, and that is the logic. Similarly, you'll get these two elements So if you'll just multiply, considering this as a row and multiply this with the entire column and add them up, these three probabilities, they would come out to be 1 by 4, 3 by 4 and 0. That is 0.25, 0.75 and 0, right? And then getting to the x3 level. Now the initial question was what would be my probability of being in state 2, right? The question asked for p 0 2 from time 0 to time 3, right? So I had taken the initial distribution to be at 0, right? That is why I took 1 1 0 for the initial distribution as x0, right? Now at time 3 I just need the probability of being in state 2, right, and not the other two. Okay, so 0 1 and 2. So I just want this probability, this one, the third one, and I don't want the first two. So let's just not at all calculate the first two and let's only calculate the third one. Okay, so this one would be, if I want to calculate x3 would be x2 into p, and we just need to calculate the third column, right, the final value. So if you'll just multiply and calculate the third value, it would come out to be, so just multiplying this as a row with the third column of the matrix P, if you'll get the value 9 by 16, right, which is your answer for P 0 to 2 from time 0 to 3, right? So this was my third method and the answer remains the same, right? So this is how we just deal with these sorts of questions, right? And this is the best method for solving them. The vectors method is the simplest one, okay, and you can deal with the most complicated of the problems using the vectors method. So I'll try to stick to this method in most of the cases now, right, because I don't need to write the complete matrix in this case, right, just the vectors. Okay, so let's take a few example questions. This is question number 3.4 from your study material. Okay, this says calculate the probability in the above model. Now this is talking about the model that we have just discussed, of starting at discount level of 25% and ending up 4 years later at the same level. Okay, so here you are starting up at 25% level and ending up at the same level, that is 25%, and after 4 years. So basically the initial distribution x0 would become 0 1 and 0, right, because now you're starting at 25% level, and now I want the probability of being at the 4% of at the same level, that is at 25% level after 4 years. So you can calculate x1 as x0 into p, right, we just did calculate it. X2 can be calculated as x1 into p. Then x3 you'll have to calculate the full value, all the three values of x3, right, at all the three levels. So this becomes x2 into p, and then finally you'll have to calculate x4, for which you'll have to calculate the probability of being at 25% level. So the first value and the third value is not required, and your second value will come out to be 33 by 128. Okay, so try it by yourself and try to get the answer, okay, and I'm sure you'll be able to. Okay, you just have to multiply these vectors with matrices and get to x4 and see the middle value, and it should be this. Okay, now let's move on to the next question. Okay, so let's try question number 3.3 from your study material, and here the first part asks, they've given us a transition matrix, right, and they have not mentioned the initial distribution, that is we do not know where do we start, right. Okay, so this is just the transition matrix in terms of p and q. Okay, p and q are some constants. Okay, so what can you say about the values of p and q? Now how do I go about solving this? See, I know that each row of this matrix should sum up to 1, right, because I know this property that the rows of a transition matrix sum up to 1, because the sum of p I j over all the possible values of j that belong to the state space is always equal to 1, right. So if you equate these three rows to 1, equating the first row and the third row, they'll give you the value of p and q. So from the third row you'll get p as 3 by 5, and then if you put that value in the first equation, that will give you q as 2 by 5, right? So these are the values for p and q, right? And then they are asking us to calculate the transition probabilities Pij3. Now if they want us to calculate Pij3 without telling us what are I and j, so we'll have to calculate them for all of these states, right? So we do not know what the initial distribution is, we'll have to calculate for all the i's and j's, right? So for that you'll have to calculate the matrix P cube, right? So you'll have to first take p square, which would be equal to p into p, and then you'll have to take p cube, which would be equal to p square into p, right? And your answer for this one would come out to be, let's just see the answer. So your answer here, it comes out to be this matrix, right? So it's this matrix. So check the values, they should come out to be this matrix. You just need to multiply it 3 times, right? You need to multiply p 3 times. And then the next part asks us to draw the transition diagram or the transition graph for the process which is represented by p, right? So you'll just have to draw the transition graph that is associated with this matrix p. P is basically 2 by 5, 3 by 5 and 0. After putting the values, half, 0 and half. And then in the third one you have 3 by 5 minus half, that is 1 by 10, and then you have 7 by 10 here, and then you have 1 by 5 here, right? So this is your process. Let's draw the transition diagram. Pretty easy. 3 states, let's call them 0, 1 and 2. Okay, so state 0, state 1 and state 2. Okay, so the probability of staying in 0 from 0, okay, so this is the state you start in and this is the one you want to go to. So from 0 to 0 is 0, it's 2 by 5, right? And then from 0, okay, 0 you can go to state 1, which is 3 by 5. Okay, similarly if you're in 1, you can go back to 0 with a probability of half, and you can go back to 2 with a probability of half. Okay, fine. And then if you are in state 2, now you can stay in 2 with a probability of 1 by 5. You can go to 1 with a probability of 7 by 10. And finally you can go from 2 to 0 2. Okay, this transition is also possible here. It wasn't possible in our example, but it is possible here. So this is given as 1 by 10. So this is your transition graph, pretty easy and straight to draw. So you can do all of this, right? Okay, so now let's just move on to the next section. Okay, so now let's consider a new type of a no claim discount model. This I'm calling as a revised NCD model. Okay, let's call this as model number 2. Okay, so let's try to consider this. So here now instead of 3 levels of discount, we have 4 levels of discount. We have 0%, same as before. We have 25%, 40%, these 3 same as before, and now we have a new level that is 60% of discount on the original premium. Okay, so this is our model now, and the rules of the model have changed a bit. Earlier our rules were that if you do not make a claim, you move up 1 level, and if you make a claim, you move down 1 level. Now the rules are that if a policy holder has no claim, he moves up 1 level, and this rule is exactly the same as the previous model. But if he makes a claim, if this policy holder makes a claim, then there can be 2 conditions. If he made no claim last year, okay, in the previous year before this, he made no claim. So he makes a claim this year, but he had no claim last year. So he will move down only 1 level, right? But if he also had made a claim last year, okay, so he makes a claim this year and then he had made a claim last year as well, he will move down 2 levels. Okay, so that is how our rules have changed for this model. So now the problem with this process is that it is not Markov anymore. It is not a Markov process, and the reason I say that is because Markov property means that you can model the future completely based on your present state, right? But in case of this, you also need to know the last year's data, that is if you made a claim last year or not, right, in order to predict the next year's claim, right? So the Markov property for any discrete time process essentially means that the probability that xt is equal to a, so given that x1 was equal to some small x, okay, small x1, x2 was equal to some small x2, x3 was equal to some small x3, so on and so forth, going up till xt minus 1 was equal to some x, okay. This probability is same as the probability of xt is equal to a given only this last value, right? So all these other values can be omitted, that is they do not matter. That is what the Markov property means. So given that xt minus 1 is equal to x, right? This is what Markov property meant, okay. But in this question this is not applicable, since your probability of, let's say, being in state 0% given xt minus 1 was this is the last value, was equal to 40%, and xt minus 2, this is the value before that, was equal to, let's say, 60%, okay. This is not equal to the probability that xt is equal to 0% given that xt minus 1 is equal to 40% and xt minus 2 is equal to 25%. Let's look at this, what this definition is saying, okay. Let's think about it this way. If a policy holder, now t is the time of the future that we want to predict, okay. T minus 1 is the present value and t minus 2 is the past, right? And this past should not matter. So both of these things, these should be equal, since this past value, it should not matter usually, but here it does, and let's see why, okay. So if you are at time t minus 2, if you were at 60% level, okay, and at time t minus 1 you are at 40% level, this first definition I'm talking about, this means that last year you had a claim, right? Last year you had a claim, that is why you moved down from 60% discount to 40% discount, okay. And if you have a claim again, you'll move to 2 levels down, that is at 0% discount. So you have 4 levels: 0%, 25%, 40% and 60%, right? And if you were at 60% level at time t minus 2, okay, you move down 1 level, at time t minus 1 you are at 40% level. If you have another claim, since you have already had a claim in this year, you will move down to 0%, okay. And this probability can be written as 0.25. that is the probability of having a claim when you are at 40% level, right? And you have had a claim in the last year, that is at 60% level, right? So this probability is 0.25. So if you had fallen down in the last year, that is if you had a claim last year, you will move down 2 levels if you have a claim this year, okay. But this probability is not same as the probability of, you were at time t minus 2 you were at 25% level, and then at time t minus 1 you were at 40% level, that is you had an increase, that is you had no claim, okay, that is you had no claim, right? So from time t minus 1 to time t, okay, you had no claim this year, that is why you moved from 25% to 40%, right? Now the probability of moving to 0%, now you are already at 40% at time t minus 1. What is the probability of moving down 2 levels? Now even if you have a claim, you will go to 25% level and not 0% level, because you will not go 2 steps down, right? Because you have not had a claim last year. So this probability is 0. So these two probabilities are not equal, and that is why this last to last value, this last year's data, it matters to predict the next year's data, right? So that is why this process is not Markov. So now we have seen that the past matters in determining the future. Okay, so past state provides additional information in order to determine the probabilities relating to the future state. Okay, so now if we want to model this process, we will need to make it Markov chain. We will need to make it a Markov chain somehow. Okay, how do we do that? We need to modify the state space of this process. Okay, so let's just look at how do we do that. Okay. So we basically had the state space here as 4 states, that is 0%, 25%, 40% and 60%. These were the 4 states that we had, and now I need to modify these states such that I can incorporate the past data into these states as well. Okay, the problem is that the last year's data also provides additional information in order to determine the future. So what I need to do is I need to incorporate that last year's data into the present state so that I have all the information needed. So the past does not provide any additional information. So I need to change the state space. So how does that work? Okay, so now I need to modify the last year's claim into the current data. Okay, so now I have 4 states already: 0%, 25%, 40% and 60%. Okay, so if you are at 0% level, okay, if you have a claim here, you will stay here with a probability of 0.25, and if you do not have a claim, you will go ahead with a probability of 0.75, and this is fine. You do not need to modify this state because you cannot move down 1 or 2 levels from this. Okay, the problem is not here. The problem is where you have a problem of moving down 1 or 2 levels, right? So here you will, even if you have a claim, you'll just be in 0% state, right? So there is no problem with this, okay, because there is no scope of moving down 1 step or 2 step, right? Okay, at 25% level, if you have a claim, you'll move to 0% level. Okay, and if you do not have a claim, you'll move to 40% level. Okay, so this is 0.75, right? So this is fine still, because even if you had a claim last year, you can only move to 0% level, and if you did not have a claim last year, you'll move to 0% level, because again there is no scope of moving down 2 levels, right? So I do not need to modify these states, right? If I'm at 0%, I'm at 0%. If I'm at 25%, I'll move down only 1 level, not 2 levels, right? So this is not possible because there's no level below 0%, right? Now if I'm at 40% level, let's talk about 40% level. 40%, if I had a claim last year, I will move down 2 levels, that is to 0%. And if I did not have a claim last year, I'll move to 25%. Right, if I have a claim, right? If I have a claim, that depends on what was last year's claim, right? So let's see how that works. Okay, so I'll need to modify the state of 40%. Okay, 40% state can be divided into 2 parts. So let's call this state as state 2, right? This is state 0, this is 1, this is 2 and this is 3. Okay, let's call this state 2. Okay, 2 can be divided into 2 parts, 2 plus and 2 minus. 2 plus means 40% level of discount given that this person did not have a claim last year. That is, he moved from 25% to 40% last year, and he is at 40% this year. That is, he did not have a claim last year. So of course he would have moved from 25% to 40% last year. That is why he is in 40. Okay, and the other part can be 40% discount given that you had a claim last year. Right, so I modified into 2 parts. This can be written as 40% 2 plus, and you can have another state that is 2 minus, right? So let's call this 40% plus and this is 2 minus, this is 40% minus. This is 40%. You are at 40% discount level if you had a claim last year. That is, in the last year you had moved from 60% to 40%, right? So this state space is divided into two parts. Now let's see about 60% level. Now if I talk about 60% level, I can move down 2 steps from here, right? If I had a claim last year, but if I am at 60% level, this in itself means that I did not have a claim last year, because I'll only move to 60% level if I did not have a claim last year, right? Because you cannot be in the top level, okay? You cannot be at top discount level if you did not have, if you had a claim last year. If I was at 40% plus level, if I did not have a claim, that is only when I'll move to 60%, right? This is only possible when I did not have a claim here, okay? And if I'm at 60% level, I'll move to this level only if I do not have a claim did not have a claim last year, right? If I had a claim last year, I'll automatically move down to this state, 40% minus, right? So if I'm at 60% level, that in itself means that I did not have a claim last year. So it in itself includes the past. So I do not need to divide this state, right? So this in itself implies that if I'm at the highest level, that means that I did not have a claim last year. Makes perfect sense. So this state does not need to be divided. So only this state needs to be divided. And let's see the remaining probability. So if I'm at 40% level, that is, I did not have a claim last year, and if I have a claim this year, I'll move down one level, that is with a probability of 0.25. And if I do not have a claim, I'll move to 60%. Also with 40% minus, if I have a claim, I'll move down 2 levels down, okay, that is to 0%. So this is with the probability 0.25. And if I do not have a claim, I'll move up to 60%, that is with a probability of 0.75. So this is what my entire transition diagram now looks like, okay? I modified the state space to allow for one more state and in order to make the process Markov. Now let's look at the transition matrix. What will it look like? So my transition matrix P looks somewhat like this. So I have 5 states: 0, 1, 2, minus, 2 plus, and 3, okay? And here also I have 0, 1, 2 minus, 2 plus, and 3, okay? Let's try to see that. So the probability of being in 0 from 0 is 0.25, moving up is 0.75, and that's it, okay? Now if I'm at level 1, okay, the probability of moving down to 0 is 0.25, moving up would be 2 plus, okay? Let's try 2 plus first and then 2 minus, 2 plus and 2 minus, okay? So moving up to 2 plus would be 0.75 if I do not make a claim, and this implies that I am at 40% level of discount given that I did not have a claim last year. So I will move to 2 plus and not 2 minus, okay? 0, 0, 0. Now if I am at 2 minus, that means, let's change this also, let's write 2 plus first and then 2 minus. So this becomes 2 plus and 2 minus. So if I'm at 2 plus level, okay, that means that I did not have a claim last year. So I'll move to 0.75. I'll move to state 3, that is at 60% discount with a probability of 0.75. And if I have a claim, even if I have a claim, I just move down one level, that is to state 1. This with a probability of 0.25, and the rest are 0. 2 minus, I'll move down to state 0, that is 2 levels with a probability of 0.25, move ahead to 3 with a probability of 0.75, and the last one, that is 3, okay? Let's try to see this. So with 3, my probability would be 0.75 to stay here, and to move down, I'll move to 2 minus, that is the probability of having a claim and then moving to 40% level. So these, all the other probabilities become 0, 0 and 0. Again we can see that all the entries of the transition matrix add up to 1. So this would be my transition matrix for this problem. Okay, so now let's take a question. Let's take a question with this transition matrix, and I would like you guys to solve it. I want you to calculate the probability of going from state 0 to 3 in 5 steps. Okay, if I want this probability. So I know that I started off in state 0, so my initial distribution with the vector would be 1 0 0 0 0. Okay, and I want to be in state 3 at time 5, right? So I'll have to calculate all the probabilities. Okay, x1 I can calculate as x0 into p. Okay, if you'll multiply this with that, it would just come out to be the first row of p. So x1 would be equal to, solve it by yourself and see the answers later. Okay, so x1 would be equal to 0 0.25, 0 0.75, 0 0 0. x2 will be equal to, it would be x1 into p, right? So x2 would be equal to x1 multiplied by p. Again, very easy to calculate. This one would be 1 by 4, 3 by 16, 9 by 16, okay, and 0 0. These values you will get if you are setting your calculator to fractions. Okay, then you have x3, which would be x2 into p, which would be 7 by 64, 21 by 64, 9 by 64, 0 and 27 by 64, right? So calculate them yourself. I'm just writing all the values. x4, if you will calculate, it would be equal to 7 upon 64, 15 upon 128, and then 63 by 256, and you'll have 27 by 256, and the final value 27 by 64. Okay, this is my last value, and now what I need is x5, and I need it for the state 3, that is the last value of this. So I don't need to calculate all of these. Okay, I'll just need to calculate the probability of being in state 3, that is at 60% level, 297 upon 512. This is your final answer. This is what you should get. Okay, so try and solve this, and I'm sure you'll get this answer. Okay, let's move on to the next topic. Okay, so before moving to the next topic, let's take a few questions from this section, and this is question number 12 from April 2011 exam. Okay, and I'm just taking a part of it. Okay, a few parts have skipped out of the question because we have not covered that portion yet. So I'm just taking part number 1, 2 and 4, and I'm skipping on part number 3 and I think 5 as well. Okay, so we'll be taking 1, 2 and 4 out of that question. 3 we'll be dealing with later. 5 is a theoretical question, so I'm skipping that. Okay, so let's just see how this works. So farmer Gills, there's a farmer who's called Gills, makes hay each year. So he's making hay, that is like for whatever purpose it may be, he's making hay, and he makes far more than he could possibly store, okay, and use himself. So he makes a lot of hay and he is not able to store all of it or use, and he does not always sell it all, and he is not able to sell it all as well. He has decided to offer incentives for people to buy large quantities so it does not sit in his field deteriorating. Okay, so he just wants to sell the hay off, okay, and he is just offering it to other people, and he has devised a discount scheme. Okay, he is giving people some discount. So he has a base price of B, okay, and that is 8 pounds per bale. So your base price is 8 pounds per bale. Okay, and then he has 3 levels of discount. Okay, and the 3 levels of discount are G, which is good if a customer is good, so he offers them a good price, that is 10% off. So this guy will be getting the hay at 7.2 pounds a bale. Okay, and then he has a loyalty price, okay, that he is offering 20% off. Okay, and he has a super price, in which case he's giving a 25% off, right? So these are the discounts he's offering, and this would bring the hay price to 6.4 per bale, and this one would bring it down to 6 pounds per bale, right? So these are the three levels of discounts. Customer who increase their order compared to the last year move to one higher level of discount. So you can think about it same as the NCD level. Now you have the four levels B, G, L and S, okay? And the customers who increase their order, okay, compared to the last year, they move to a higher level of discount. Customers who maintain their order from the last year stay at the same level of discount, okay? So you can stay at the same level of discount, you can move up. And the customers who reduce their order from the last year drop one level of discount or remain at the level B, provided that they maintained or increased their order the previous year, right? So they'll move up one level if they'll move down one level of discount if they reduce their order, provided that they had maintained or increased in the last year. Okay, so if they maintained or increased in the last year and then they reduce it this year, they'll drop down only one level. Okay, and the customers who reduce their order from the last year's, they drop down two discount levels if they had also reduced their order last year. So last year also reduction, if you're reducing this year again, then you're dropping down two levels. Okay, subject to the lowest level of B, which is the base price. So that's the lowest level. Explain why the process with the state space BGLS, this is the normal process which we would expect, does not display the Markov property. Okay, so it does not display the Markov property because the drop down depends on the last year's purchase. Okay, if there is a reduction in 2 consecutive years, there'll be the person will fall down 2 levels. So you can write this as the probability that you are at B level of discount, given that let's call it xt is equal to B, given that you at time xt minus 1 you were at L level of discount and xt minus 2 you were at G level of discount, right? So this is if you had increased last year and then this year you are reducing. Okay, this probability is not same as the probability that xt is equal to B, given that xt minus 1 is equal to L and xt minus 2 is equal to S. Okay, so if you were at G level of discount and then you move to L, that means you increased. So now you cannot fall down 2 levels, right? You cannot fall from L to B. You'll first go to G. So this probability is basically 0. This is an impossible event. But if you are at you were at time t minus 2 you were at S, then you fell to L. Okay, now you will fall down 2 levels if you again reduce. So this will have some probability. So these two probabilities are not equal and this past state is affecting this process, and that is why this is not Markov, because our discount level depends on the past sales as well. Okay, define any additional states required to model the system with the Markov property. So what is the additional state that I need to introduce? So I need to the maximum level of discount is S, the minimum is B. Okay, so if you are here, it already means if you are in S, it means that you increased your sale or maintained your sale last year, right? That is what it means. So there couldn't have been a reduction if you are at S. If you are at B, you cannot fall anymore. If you are at G, you can only fall down one level. the only state we need to modify is S, because from here you can fall down one level or two levels, right? So L is the state that I need to modify. So L will be in two parts. It would be L plus discount level L was let me check, it was 20%, I guess. Yeah, 20% level of discount. Given that the customer increased his order last year, increased or maintained? Right? And L minus would be equal to discount level L, that is again 20%, given that the customer reduced his order. Right? So now our state space becomes, which they had asked us to write, is it's B, which is the base price, G level of discount, L minus level of discount, L plus level of discount, and finally S level of discount, right? So this is our state space. Now let's look at the next part. So the next thing that they have told us is that Farmer Gillis thinks that each year customers have a 60% likelihood of increasing their order and 30% likelihood of reducing it. That means 10% of maintaining it at the same level, right? So these are the three possibilities that can happen: 60% for increasing, 30% for reducing, and 10% for maintaining discount in any current year. Construct a transition graph of the Markov process, clearly labeling all the states. Okay, so let's do this. So I'm trying to draw the transition graph here, and I know that the probability for reducing is 0.3, increasing is 0.6, and maintaining is 0.1. Okay, so let's try to label all the states. So we have B, that is the base state. You have the good level of discount. You have L plus, that is loyalty plus. You have L minus, that is loyalty minus. And then you have the super discount, right? So let's start with B. Now if you are at B, you can do three things. You can either maintain, increase, or reduce. So if you maintain, you stay at the same level of discount, and if you reduce, you still stay at the same level of discount. And the reason for that is that you cannot go any further down from B, right? So in either of the cases you stay here. So reducing and maintaining probabilities add up to 0.4. If you increase your order, you get to G, that is 0.6, right? Next, if you are in G, okay, then you can either increase, reduce, or maintain. If you maintain, you stay here, so that is 0.1. If you increase your order, then you get to L plus, that is 20% discount, and you have moved up, right? So that is for increasing, that is 0.6. And if you reduce your order, you go to B, which would be 0.3. So these are my probabilities. Now let's say I am at L plus, that is last year I increased and now I am at loyalty discount. Okay, so last year I increased or maintained, right? So if I increased or maintained, okay, if I maintain this year, I will stay here. Of course, if I maintain, I'll stay here. And if I increase my order, I'll get to S, of course 0.6. And if I reduce my order, I'll get to G and not B, I'll get to G, because I increased last year. That's why I'm in L plus. Okay, so reduction gets me to G, right? Now let's say I'm in L minus. Okay, now I can have three things. I can increase, reduce, or maintain again. Okay, if I increase, I get to S, of course. so that is 0.6. If I reduce, I'll go directly to B because I fall down 2 levels, that is 0.3. Now, but if I maintain, I'll get to L plus and not this state itself, because that would mean I am at loyalty discount and I maintained. And they have already said that if you are at loyalty discount and you increase or maintain, you'll only fall down 1 level. So L plus, we had defined L plus this way. See, L plus was defined as discount L 20%, that is the customer, and given that the customer increased or maintained. So if you maintain at the L level, you'll get to L plus, right, and not L minus. L minus is only if you get to L and you have reduced, right. So this would be 0.1. And now if you are at S, okay, let's see S, that is the last one. So if you are at S, you maintain, you stay here, that is 0.1. You increase, again you stay here, so that becomes 0.7, 0.1 plus 0.6. If you reduce, you get to L minus, which would be 0.3, right. So this is what my transition diagram looks like. In the next part, they've asked us to make a transition matrix, which I can easily make. So this becomes all B, G, L plus, L minus, and S finally. Okay, so from B, if I think about B to begin with, I can stay here with a probability of 0.4. I can go up to G with a probability of 0.6, and all the other 3 become 0. Okay, if I'm at G already, I can reduce with a probability of 0.3, stay here with a probability of 0.1, and get to L plus with a probability of 0.6, and the other 2 are 0. If I am at L plus, I can increase with a probability of 0.6, I can maintain with a probability of 0.1, and fall down 1 level only with a probability of 0.3, right. If I am at L minus, that means I can go up 0.6, I can fall down 2 level, that is 0.3, and I can go to L plus, that is maintain with a probability of 0.1, and the other 2 guys are 0. Okay, so that is how I calculate my probabilities. And the last one here becomes if I'm at S, I increase or maintain 0.7, I go down to L minus, that is 0.3. So all the other ones are 0, 0, 0, right. So this is what my transition matrix looks like. Okay, so I just realized that for solving the fourth part of that question, we need to do a few more topics. So I'll get back to that after we do a few more topics. Let's move on to the next topic now. Okay, I'll probably solve that question in the next video on this chapter. So this chapter is going to be of 2 videos. In the next video, we'll cover more topics. Okay, so for now, I'm discussing a new topic, that is simple random walk. Okay, so I'm trying to discuss a topic from the chapter 2, stochastic process, as a Markov chain. Okay, so if you remember the simple random walk, the process was basically the sum of a white noise process. Okay, we had discussed that was general random walk, and when we had the white noise process, yt as +1 with the probability of p and -1 with the probability of 1 minus p. When we had this process, and when we added these processes yt's, when we added these processes, let's call them yj, where j goes from 1 to t, when you add them, you get a process xt, where you can take maybe x0 is equal to 0. So you start from 0 and then you add +1 or -1. That process is a simple random walk, right? So I've already discussed this simple random walk in chapter number 2, and I have given you 2 definitions for it. Either it can be seen as the sum of this process, this white noise process, or you can see it as xt is equal to, based on the previous value, that is xt minus 1 plus 1, that is it will be 1 more. Okay, you'll add 1 with a probability p, or xt minus 1 minus 1 with a probability of 1 minus p, right? This is what my simple random walk used to be. Now I'm gonna show you that it is also a Markov chain. First thing, there are a few criteria for a Markov chain. So first thing you need to realize is that for a simple random walk, the state space is discrete. Okay, the state space is discrete. Why? Because the state space can be, it starts from 0, and then on this side it can be -1, it can be -2, -3, so on and so forth, right? It can either reduce like this, okay, but it can only take these integer values 1, 2, 3, so on and so forth, right? So this state space, it is discrete, and it is an infinitely extending but discrete state space. That is, it can only take these fixed values and not values in any interval, right? And my time set will also be discrete. So my time set would be, it would be defined at time 0, 1, 2, 3, so on and so forth, right? So the time set and the state space are discrete, and the probabilities xt only depends on its previous value, that is xt minus 1, right? So this is a Markov process. This only depends on its previous value. So that is why it is a Markov chain, and that is why I can say that a simple random walk is also a Markov chain. Now let's try to look at the transition graph of this process. So what will the transition graph of a simple random walk look like? So you start from from 0 as your state, and then on this side you can have a -1, you can have a -2, you can have a -3, so on and so forth. These states will keep on going. This side you have 1, 2 and 3, and this state, these states will keep on going, okay? So the probability of moving forward is P, and the probability of moving backward is 1 minus P, right? So you just move forward with the probability of P, and you move backward with the probability of 1 minus P. So if you are at 0, you will move to 1 with the probability of P, and you will go back to -1 with the probability of 1 minus P. Same for all the values. So you move forward with P, you move forward with P, and you move forward with P, and even from the previous value, okay? And then again you move forward with P, you move forward with P, and then you move forward with P, right? And if you want to move backward, you get from -2 to -3, this would be 1 minus P, again this would be 1 minus P, and then again this would be 1 minus P, and again 1 minus P, and again 1 minus P, right? So this would 1 minus P, and this will extend forward, okay, 1 minus P. So this is what my transition graph looks like for a simple random walk, right? That is what it looks like. If I talk about the transition matrix, okay, transition matrix would extend infinitely as well, because it has infinite states. So it would extend infinitely. Supposedly you are in a particular state, the probability of staying in that state would always be 0, because you either move forward or you move backward. So the probability of moving backward would be 1 minus P, and the probability of moving forward would be P. For the next state, the probability of staying there would be 0, going back is 1 minus P, moving forward is P, okay? Similarly, for the next state, moving forward is P, staying here is 0, moving backward is 1 minus P, and so on and so forth, right? So you can model all these probabilities, and this is what my, okay, you'll have to write the same things here as well. So this is what my transition matrix would look like, right? This is what the transition matrix looks like. So it would extend infinitely, just that the probability of going back would be 1 minus P, and going forward would be P, okay? So now let's talk about, what about if you want to transition from state I, any particular state I, to any particular state J in n steps. You want the n step transition probability, right? If you want to get from any state I to any state J, you want the n step transition probability, okay? So how do I calculate that? Okay, now think about a simple random walk, and think about this, that you can only have increases or decreases in this case, right? You can either have upward movements or downward movements, that's it. So all of these n steps, they'll comprise of, if I want to, I can go back from here, I can go forward and then back, and then back again, and then forward again, and only one step, right? Each transition would be just one step. Okay, so I can take steps backward and forward. So the total number of steps that I take, steps that I take would be equal to n. So let's call all of my upward steps as u. U are all my upward steps, right? That is all the increases. And let's call all my downward steps as d. Right, so u are all my upward steps and d are all my downward steps, right? So this would mean that the total distance that I want to cover is j minus I. It would be j minus I, of course, because these are all integer values, right? The state space is comprised of all integer values, these integer values. And if your I is 0, you're starting at 0, and your j is, let's say, 50, the total distance you want to cover is of 50 steps, right? So your j minus I would be some integer, right? So your total number of steps is basically n. So it would be u plus d is equal to n, and the total distance you want to cover would be all the upward moments minus the downward moments. That is, the net distance you have to travel is all the upward moments minus the downward moments, right? So u minus d would be your upward moments minus downward moments. That is the amount of gap that you will cover, and this will have to be equal to j minus I. That is the total distance you want to cover, right? So if you want to go from I to j in n steps, you will take u upward steps and d downward steps, and u plus d would be equal to n, that is the total steps, right? Total steps. And u minus d will be equal to j minus I, that is the total distance covered. So this can help me to do something. This is a equation in two variables, right, u and d, and it can help me calculate the values of u and d in terms of n, I and j, right? So let's try to do that. So if I try to solve these two equations, this is equation number 1, this is 2. If I add 1 plus 2, if you add these two equations, it becomes 2u is equals to n plus j minus I, right? That is what it becomes. Now u will be thus be equal to n plus j minus I by 2. And if you try to see your d would be equal to, from equation 1 you can say it would be equal to n minus n plus j minus I, right? N plus j minus I by 2, right? You'll have to deduct it from n, right? That was d. So that would be n minus u, right? And that's equal to n minus n plus j minus I by 2. So this would be equal to n minus j plus I by 2. This would be equal to my value for d, right? So I have to take these steps. I'll have to take n plus j minus I upward steps and n minus j plus I downward steps in order to get from here to, I to j in n steps, right? So my probability of getting from I to j in n steps, right? Now these steps, okay, all these steps, plus ones and minus ones, they can occur in random order, right? They can be plus ones and so on and so forth, right? So they can occur in a random order, okay, one after another they are occurring. So what would be the probability of getting from I to j in n steps, right? So these can be arranged, okay, they can be interchanged, right? So they can have different orders. For example, if you have 5 steps, you can have plus 1, minus 1, plus 1, minus 1, plus 1, right? Still the same values. I'm taking 3 pluses and 2 minuses, okay, that's what I'm taking here. Let's consider how can they happen, okay? 3 pluses and 2 minuses. So you can have a minus 1, plus 1, plus 1, plus 1 and minus 1. And you can have a plus 1, minus 1, minus 1, plus 1, plus 1. So you can have them in different orders, right? They can arrange in different orders. Okay, so that is something we need to understand, right? So I need to accommodate their order as well, right? So 3 pluses and 2 minuses. Okay, that's what I'm taking here. Let's consider how can they happen. Okay, 3 pluses and 2 minuses.
You can think about the
so
U upward movements as U successes.
Plus
right?
1, plus 1
Out
and
of
minus 1.
n moments you want U successes and n minus U, that is D
plus
failures.
1, plus 1. So you can have them in different orders,
downward
right? They can arrange
and
in
the
different
probability
orders.
of each
Okay.
success, that
So
is
that is
upward
something we
movement
need
is
to
P,
understand,
and
right?
the probability of each
So
failure
I need
is
to
1 minus
accommodate
P.
their
We have
order
already
as
seen
well,
that the
right?
probability
So you
of an
can think
upward
about
movement
it
is
as
P
a
and the
binomial
probability of downward
distribution.
movement
What
is
we are
1 by
doing
P.
is,
So
I want
one
U
minus
upward
P. So you
movements
can
out
look
of
at
n.
this
I
as a
want U
binomial
upward
distribution.
movements.
So out of n
and
movements, you
D
want
downward
U successes
movements,
or U
right?
upward movements.
Okay,
right?
that is what I want.
So that's how we'll model it.
So the probability of getting out of n moments U upward movements is NCU. Okay, it would be NCU, P to the power of U and 1 minus P to the power of n minus U. This would be the probability of getting U upward movements. Now P is the probability of upward movements. We have already seen that the process takes a value of plus 1 with the probability of P and minus 1 with the probability of 1 minus P, right? So you'll have P upward movements, and with 1 minus P you'll have n minus U, that is D downward movements, right? So that is how it will function. Okay, and this is how you can calculate the probability of getting from I to J in n steps. But this would only be true if U is an integer, because number of integers, number of steps will have to be integer number of steps. You cannot have 7.5 or 6.2 steps, right? You cannot not have numbers like that. So this will have to be an integer. That means n plus j minus I. Okay, this will have to be even. Okay, this will be an even number, right? That is one thing. This thing, it will have to be an even. That is only when U, that is n plus j minus I by 2, will come out to be a integer, right? And the other consideration is that the number of steps should be between 0 and n, right? Number of upward movements, that is, they should be less than n. Like if you want to go from I to j in 20 steps, you cannot take 30 upward movements, right? Okay, so U will have to be between 0 and n. That is another consideration. So n plus j minus I by 2 has to be between 0 and it has to be less than n. Okay, it has to be between 0 and n, right? So this is another consideration. So another way I can write this is n plus j minus I is between 0 and 2n. Okay, so if these two things are true, that is only when I can apply this definition, right? This definition for Pij, probability of getting from I to j in n steps, can be evaluated using the binomial distribution only when these two considerations are true, right? It would be equal to 0 otherwise. If these two considerations are not true, then the probability becomes 0. That is, it becomes impossible to transition from I to j in n steps. And we have already seen the probabilities relating to the simple random walk in the previous video, right, relating to stochastic processes. There we calculated the probabilities for transition, right? And I told you there itself that there is a easier method, okay? And this is that easier method that we can just evaluate it using the binomial distribution, okay? But this will only be true when n plus j minus I is even and this n plus j minus I by 2 is between 0 and n. Otherwise, this formula, it is not possible to apply, okay? And we have already seen such cases in case of simple random walk in the last video. I don't know if you remember. There was a case where we solved it and it was impossible to get from a particular state to another. Okay, so let's take examples of this. How will we apply this formula now? And let's try to see how to do it mathematically.
Okay, so let's try to calculate all these probabilities. So the first one is the probability that x20 is equal to 15 given that x0 was equal to 0. Okay, so this can be represented as p 0 20. Okay, now I want 15, so 0 to 15 from time 0 to 20, right? This is what I want to calculate. Okay, so for this let's just see what are our values. Okay, we have got our we want it to happen in 20 steps, so n is equal to 20, then you have got j which is equal to 15, the value you need, right? I comma j, so okay, and I is equal to 0, right? So let's check for the first two conditions that we have first of all. Okay, so first thing that we need to check is n plus j minus I should be even, right? It is 20 minus 15, this 15 plus 20 plus 15, that is 35. This is not even, right? So this probability, this entire probability, it becomes 0. It is impossible to get from 0 to 15 in 20 steps. It is impossible, okay, because this probability, it does not come out to be even, right? It does not come out to be even, so we cannot do it. So n plus j minus I has to be even for this to happen. Okay, so this one is 0. Okay, now let's just see the second one. Now for this one, let's check everything. So here n is equal to, I want it to happen in 20 steps again. Okay, j is equal to 16 and I is equal to 0, right? So n plus j minus I is even this time. So n plus j minus I is 20 plus 16 minus 0, that is 36, that is even, right? And the second thing that I need to check is n plus j minus I should by 2 should be less than n, right? So n plus j minus I should be n plus j minus I by 2, that is 36 by 2, should be less than n. So that is just 18, which is less than 20. So this is less than 20. So this is also possible. So both the conditions are satisfied, yes. So I can calculate this probability. So this probability simply becomes 20c. Now what would be my value for u? U is basically equals to n plus j minus I by 2, that is 18. So 20c 18, p to the power of 18 and 1 minus p to the power of 2. Okay, so this is how I can calculate it. Say supposedly I know that p has a value of 0.95. Let's just say that I know the value of p. Okay, so if p is equal to 0.95, this value becomes, you can calculate it on your calculators, 20 c 18 p to the power 18, that is 0.95 to the power of 18, and into 0.05 to the power of 2, right? So this probability, it comes out to be 18 point something percent, 0.1886768, right? So this is the probability that you get from 0 to 16 in 20 steps, right? This is your probability. Okay, let's check the last one. So we have solved 2 parts already. Okay, let's check the last one. So this is the probability of getting from 0 to 38. Okay, this is 0. Probability of getting from 0 to 38. I am in 0 at time 0 and I want to get to 38 at time 36, right? So this is the probability that I want. So this can be written as probability of getting from 0 to 38 from time 0 to 36, right? So you should get this, that the subscripts that are written, that this can be basically represented as xt is equal to some k, right? So you should get that the subscripts are time and this is the state value, right? So this is the probability that I want. Now n is equal to of course it is equal to 36 here, the number of steps. I is equal to 0 and j is equal to the state I want to be in, that is 38. Okay, let's just see, okay, for if both the conditions are satisfied. First, n plus j minus I is even. Yes, 36 plus 38 minus 0 is even, right? So this condition is satisfied. Let's check the second one. Now the second one says that n plus j minus I by 2 should be less than 2n. So if I add these two, 36 plus 38 minus 0 by 2, okay, this should be less than n. This should be less than n. So 36 plus 38 by 2 would come out to be 37, which is greater than 36, right? So this is not true, okay? So this probability is equal to 0. So I can directly write this probability as 0. So that is how you just apply these conditions, okay? And that is how you calculate these probabilities. Pretty straight to calculate. I have shown you the derivations as well, okay? It's just you just apply, think about the number of movements that you want, and then you apply the definition, okay? So let's move on to the next topic now. Okay, so next and the last topic for this video is called as boundary conditions. Now we have seen some Markov chains which have an infinite state space, including the simple random walk. Okay, there are processes which can have an infinite state space. So for these processes we need to impose some boundaries sometime. For example, we had our simple random walk. It is going from 0, 1, 2, 3, so on and so forth this way, and on this side this is going to -1, -2, and so on and so forth, right? With probabilities of moving forward as p and moving backward as 1 minus p, p and 1 minus p, right? Similarly here it was p and 1 minus p, and so on and so forth, right? So I had all these probabilities, and this is an infinite state space process. It would keep on going, okay? So let's assume that I do not want this process to go negative, okay? I want to create a boundary here somehow, right? I want to create a boundary here somehow, right? So I do not want this process to go negative. I want it to exist only on the positive side, okay? And maybe at some integer point b, I want to impose this boundary on this side, okay? So I don't want it to be greater than b again. So this is how I can restrict my process. I just make a boundary here. Now with boundaries, the thing is that you cannot just draw boundaries, you need to define them mathematically too, okay? You cannot just say that I've drawn boundaries and I'm done, okay? You need to define them mathematically, and mathematically we have 3 types of boundaries, okay? And these boundaries, what they do is they do not let the process go beyond these points, right? So the first boundary that we have is called as the absorbing boundary, right? Absorbing boundary, as the name suggests itself, it means that once the process reaches there, it stays there, right? It cannot go anywhere beyond that or anywhere else, right? It just stays in that particular state. So how can I define this? Let's say at 0, if I'm defining the absorbing boundary at 0, this would be defined as probability that xt is equal to 0, given that xt minus 1 was equal to 0 is 1. So once you reach 0, your process reaches 0, it stays at 0 with a probability of 1. So probability that xt minus 1 was 0 and then xt is 0 is equal to 1. So after this, every time once you reach 0, you'll keep on being at 0, right? So this is how you can just define this boundary, right? So if at any point of time you reach 0, then you will perpetually keep on having 0 if you have defined a boundary like this, right? This is one boundary. This is called as the absorbing boundary. Best example of this is, let's consider some guy who's playing a game, okay? And if this guy is playing a game, he'll play it until he'll be ruined, okay? So let's say he starts with a certain pot of money, and then he will play it until he reaches his target of b, or he is ruined, that is at 0. So once he reaches 0, he is ruined, or he reaches his target of b, he'll stop playing that game, right? So the gambler will stop playing his game, if he reaches 0 or he reaches B. So I can define two absorbing boundaries at B and at 0. Okay, so the absorbing boundary at B can be defined as a probability that xt is equal to B given that xt minus 1 is equal to B is also equal to 1, right? So this is how you can just define an absorbing boundary. Now no one can go anywhere else from this place, right? This is an absorbing boundary. Let's talk about the next type of boundary, that is called as a reflecting boundary. So a reflecting boundary just reflects, okay, it reflects back. It does not absorb, it reflects back. So let's say I get to 1, let's say I get to 0. Now my probability of going to -1 is 1 minus p, and going to 1 is p, right? Now let's say I want to make a bouncing boundary here, or maybe a reflecting boundary. So I want this process, as soon as it reaches 0, I want it to come to 1 again, okay? So as soon as it reaches 0, it gets to 1 with a probability of 1. So all the probability is directed this way. So an absorbing reflecting boundary looks somewhat like this. At 0, if I am defining this, this becomes probability that xt minus 1 becomes 0, then next value comes automatically 1, and this probability is defined as 1. So if it reflects, if it reaches 0, then it will immediately become 1, right? This is a reflecting boundary, okay? The third one is called as a mixed boundary. It's a combination of these two, right? So mixed boundary is partially an absorbing boundary and partially a reflecting boundary, but it does not let the process go below this point, okay? So it can have some probability of absorbing, and then it can have some probability of reflecting, okay? So let's say the probability of reflecting is alpha, okay? Let's say it's alpha. So the probability of absorbing would be 1 minus alpha. So in a few cases it will absorb and then it will reflect, okay? We have seen boundaries like this. When I used to define my NCD model, 0%, 25% and 40%, when I used to define this, I used to have a mixed boundary here and here, right? It used to reflect as well as absorb. So I had arrows which were directed at 0 again, and then some arrows which were going ahead as well, right? So I had a reflecting boundary here as well, right? So this is something we know, right? So I can have a reflecting boundary like this, okay? A mixed boundary like this, right? So mixed boundary at 0 would be defined as probability that xt is equal to 1 given that xt minus 1 is equal to 0 is some alpha, and the probability that xt is equal to 0 given that xt minus 1 is equal to 0 is equal to 1 minus alpha, right? So these two are the probabilities, and this is how we define a mixed boundary, okay? So these are various kinds of boundary conditions that we can have here, okay? So this was all for this video. Thank you very much, and then we'll discuss the rest of the topics in the next video. I hope you enjoyed the video. Thank you.